Okay. Good afternoon. So it is a pleasure to have here in Bologna Elisabetta Caffau and Piercarlo Bonifacio. They are visiting us for 1 week, and they are in the guest office on the 3rd floor. So in case you want to ask them questions after you listen their seminars, you are welcome to keep in touch with them and come to the guest office. And they will both give a talk today. So we have these 2 talks, and let's start with Elisabetta by Carlo. Elisabetta graduated. Elisabetta got her PhD in the Observatoire de Paris, where she's now working. Actually, her formation was not in astrophysics initially, and she also spent some time in teaching, and then she came back to research. So quite peculiar career path. And she discovered one of the most metal poor stars in the Milky Way that for quite a long time has been the most metal poor stars known in the galactic halo. Is the Caffau star, so it's great that you have a star with your name. But her talk today is more related to Gaia and the calibrators. She talks about Gaia and the science that you can do with these calibrators.
Thank you. So thank you very much, Nandella, for introduction and for having me here. I really love Bologna, so anytime being here is a pleasure. Yes, in fact, today I wanted to move a bit on something more, let's say, technical or support, perhaps. The reason is because I'm in my laboratory. Gaia has a big impact, money-wise, time-wise, and etc. The coordinator of the CU6 is in my laboratory, so meaning that we try to work on it. Also because I think we all agree what is Gaia nowadays. Gaia is providing us a lot. Information on more or less 1% of the stars in the galaxy, and is giving us breakthrough. So for me, working in whatever is helping to having better data for me and for you, I find important, essential. Meaning that tomorrow you will have perhaps better data because also I work on it. But also I try to do some science with it. Sometimes because I make some effort to do that because I have good data, let's try to do something interesting. And sometimes because I try to validate, like, wow. So these are the 2 aspects that sometimes I search for some science, and sometimes I find it without searching for it. So not much words on Gaia, because I know Gaia is also home here very much. You're very much involved also in this one. I would like just to recall one big time in few months. We will have a celebration for us, meaning 10 years of data taking for Gaia in the National Day of France, 14th July. So it's just now 10 years that Gaia is working. So Gaia has 3 instruments on board. So I think you know us: an astrometric instrument, a spectrophotometer, and a spectrograph. In my institute is centered on the spectrograph, the Radial RVS, Radial Velocity Spectrograph. So I concentrate only on this one, also because I can help there, I can't help anyone else. So the RVS wavelength range is small, large, big, and etc. I know it's subjective. But from what I'm used to, this wavelength range is small, as this resolution is a low resolution for me. I know people say it's middle resolution. Yeah, it is low anyway. Which is the problem? We are trying to derive radial velocity from data with spectra with a wavelength range smallish and resolution lowish. And just to have an idea why small, why low, etc. Recently, the spectrograph built to have a fantastic radial velocity in accuracy and precision is espresso. Extremely high resolution and extremely large wavelength range. So Gaia has a limitation in this side. So we should help in this way. Also, RVS is a self-calibrated instrument, meaning that we need something on ground. for the line spread function and also for the zero radial velocity point. So this is where I'm entering and helping. I'm not the first one, of course, because Caffau et al. And Subiran et al. Starting collecting data to help Gaia. So ground observation with what is called the radial velocity reference stars. They started long ago to collect stars. There are papers on that, and there are less than 3,000 stars on that. And later on technical notes, there are other stars. Laurent Chemin put a lot of effort on collecting data, but these reference stars for the RVS, it's not obvious that the wavelength range used is the same of Gaia. So what I said is, okay, to try to improve it, what we can do, observe more stars, possibly exactly covering the wavelength of Gaia without Gaia. And so this is what I did in several ESO periods. All in all, I had 8 program approved. My goal was to have exactly the wavelength range of Gaia in one way, and combined with something bluer. The bluer we go, the more lines we have. So to have tomorrow a comparison, what do I deduce and radial velocity on the red arm and on the blue arm. So we combine it with the 437. Goal was 1,000 targets. We have it nowadays. Bright. We are observing these stars in the magnitude 8, 9 with UVES. Yeah, I know, it's absurd. Yes. But in one OB of 20 minutes, less than half an hour, I have really great spectra. The idea also was to have something to leave for other people. Good data in the ESO archive. So tomorrow someone can use these data to compare to something fainter, to check some physics on these stars. One espresso run is going on, started just now, and it's almost finished. This is just 39 stars that we observe just to have really the 0 point to compare to the UVES data, then to compare to the RVS spectrum. So this is the goal we will have. So target selection, how so? I changed it. Any period was different because I have to decide what is best for Gaia and what was needed for Gaia. The first period I started something very easy. Good target for which Gaia obtained a radial velocity with a very good uncertainty. So 80 giants, very smooth and easy. Then I started on the following 2 periods to add some stars with large uncertainty for Gaia, because why so? What's wrong with this star? To try to start understanding what's wrong with the stars with the Gaia radial velocity determination. In the following period, we added also some stars with high absolute value radial velocity, again to check, is Gaia wrong or not? And so this is more or less changing, and the period, the latest period was the espresso. And anytime I try also to add it stars selected in Ra and Dec, so to try to fill as much as possible Gaia's plane. So this was more or less the strategy. Other selection were unknown stars, stars for which there was no complete chemical inventory. So to leave something in the Gaia archive and in the ESO archive for the following people to use them. So I would like this program to have a legacy in the future. So this is the first period. This is already published because we wanted to present it and so on. There were 80 giants, I would say metal rich, perhaps you would say from solar to slightly metal poor. So selected, these are a good sample, no problematic, and yeah, that's true. And this is, so what did I want? I wanted just to have these stars as soon as possible in the archive for the RVS to be used in the Gaia data release 4. This one has been already used in data release, the next one. But what can I do with good data? I'm not really fascinated by metal-rich stars, that's true. So I had to think about. But rubidium, in fact, is not very much investigated. Few lines in a stupid wavelength range. So why not checking rubidium? Yes, we checked rubidium. Why rubidium from a scientific point of view? Because it's interesting. This is formed in R and S process both, But the ratio of the two isotopes of rubidium, 85 and 87, one is stable, the other one is long life. The ratio of them is dependent on the density of neutron on the site of production. So fantastic, I could measure the ratio of the two and derive the neutron density. No, not really. This is a heavy element, so no way, we can't do that. But what we can do is to compare the abundance of rubidium with respect to the neighbor elements, strontium and yttrium. The higher the ratio, the higher the neutron density in the place of production, and vice versa. So this is how we use it. And okay, the result is uneventful, that's true. So this is a base sample of star, you see extremely metal rich, but this is what we need to present. To compare to the Tompkins-Lambert, so we agree pretty well, I would say. And this is the comparison with the great analysis of Takeda, very recent one. And well, this is a bit more puzzling for me, because we agree on the metal poor side, but not in the metal rich. I don't know why. It's low statistics. I don't know. I mean, I was a referee of this paper, so I really studied it, and I think it was a great work, but there is slight disagreement. I will improve, I hope, statistic with the next runs and try to understand is a statistical problem is something back on that. But okay, so rubidium was something that could be done on with this respect. If I compare rubidium with yttrium and strontium, nothing to be said. So these stars are found no extremely high density, neither low, and so on. There is one exception, a star which is very low in rubidium with respect to the neighbor. How so? Well, in fact, the star is normally rubidium and is high in the other heavy elements. So this is it. And not giving the information I would have liked to look for. The following period, or the following interest I triggered was highlighted by David Katz. The problem of David Katz was validating the RVS result measurements, and the radial velocity sometimes provided by Gaia was very high, larger absolute value of 500 kilometers per second. Do we believe in that or not? Well, we have to validate. So we put some stars to be observed in the following periods, and to try to have good data, or at least sufficient to have validation or not of Gaia. The stars are much fainter, but we are speaking about 10, 14, so bright for UVES. We observed a sample of them, 43, and also we observed a sample with Sophie in south of France. Quality of the spectra, I would say, is good, from very good. They are going very good in the archive for the validation of the DR5 at this point, to okay. Of the 45 stars, I analyzed 43. Why not all? Because one is a carbon star, so very complicated, etc. Was known to be a carbon star. I just wanted to see the radial velocity. And one is active and variable. What about the others? Well, more or less, you could say uneventful, but uneventful in a very peculiar kinematic way. We are speaking here about high-speed stars. The kinematic is a bit extreme. This is just radial velocity. Yes, I know, but if you add also very tiny speed, or sorry, transversal velocity, they are really high-speed star. So something that shocked me the first time I selected from a scientific point of view, high-speed star, in that case was speed, I always ended up with this range in metallicity. Why not extremely metal poor star? Never. I have in a large sample, 1 or 2 just below -3. How so? So they are metal poor. When I select kinematically, they are just metal poor. This is extremely interesting. Something interesting is also I selected 3 candidates that are possible or compatible to be Pisan descendant, and 2 apparently young stars. So this is more or less the inventory. Another one, this one was for me a normal star, but in fact Rodrigo Ibarta told me that this is associated to a stream, one of the stream he found out. So I found it extremely interesting to have the complete chemical inventory of for a star belonging to a stream. So the variable star, yeah, it's really variable. I had for this one by chance 2 spectra, so it's really lucky. And this is according to phase, the variability of the G photometry. So yes, this is a variable star. It's not much I can do. Of course, I could try to have the temperature in each spectrum and observe it and analyze. Yeah, in the future, if someone interested, why not? At least the star is known and in the ISO archive. The 2 young stars, well, a young star, why not? They are definitely younger than 1 gigayear, but they are -2. How so? How can I have a metal-poor young star? This is not the first time I find metal-poor young stars with Perkarlovich and others, but again, is it possible? Of course, I'm in Bologna, and the answer will be blue straggler. Perhaps, but one of them, I don't remember which, I think this one, has the corresponding mass just below 2 solar masses, 1.8. So could be. I have 2 stars. No, don't lose any mass. Okay, the other one is 3 solar masses. What do I need? 4 stars to form this one, to find the 3 mass stars here and not already evolved? Unlikely. So I think really, I insist, because I wrote papers in the past, that there is a population of metal-poor stars young, so meaning formed recently. And this is, I find it really exciting. For anything else, there is not much that can be said comparing the sample to the blue ones. To other sample, the red one of this famous sample by Cairel et al. Large program, and the pink is Ishigaki. So the stars are very normal from any respect. This is what I expected, of course. I didn't expect anything strange. Of course, yeah, some are, there is a usual scattering in sodium, of course, and one of the stars is low in copper. This is the pism possible descendant. And of course, 2 of them, they have to be 3 of them. Sorry, there are 2 of them, one on top of that, but these are 2 of them. Low in zinc. So 3 stars are apparently pism descendant. If I compare, I put in this plot, there is one of the pism descendant candidate. So a star low in zinc, normal in zinc, and cross rich in zinc. And I compare to the yields by Hager and Woosley. This is what I would expect from pism descendant. And you see my values as much larger. So yes, but I do not expect this star to be descendant from a material completely enriched by a pism, but just diluted in some other materials. So there was also a pism enriching the material from which these 3 stars formed. From anything else, the stars are normal. This is barium of the opium compared to the sample of Cairel, so not much to be said. I was having this good spectra of slightly metal-poor solar, but the quality was good enough to derive carbon. So I derive from G-band carbon, as of course carbon is low because majority of the stars are evolved. So of course carbon has been converted in nitrogen, so I don't measure, I don't have nitrogen, but I have carbon, and carbon is low. Okay, except this star is on the turn off, so carbon is normal, slightly enhanced as expected, but the other not. Honestly, I'm not an expert on metal-rich stars, and of course, I'm not an expert in dilution and mixing and so on. But in my naive point of view, I thought, okay, I should have some sort of correlation, surface gravity, carbon over iron. I expect something more, a correlation, a tighter correlation. I would say this is a scatter plot. So, meaning that when carbon is converted into hydrogen, is much more complicated than just evolution and logic. There is something more, but it's not my cup of tea. So this was my exercise and my understanding on that. We are speaking about fast stars. This is really fast stars. This star was selected outside Gaia. it was in our project on looking for high-speed star to understand how they are and so on, and was selected because his speed was high. Yeah, 1,400 kilometers per second. Do we believe in that? I don't know. So the idea was, why not try to have UVES data and to try to understand, is possible that the Gaia parallax is wrong? Why not? It's possible. So with the two spectra, I tried to derive the surface gravity from the two spectra and try to have a parallax from the surface gravity. I mean, try to have an understanding if the parameters I derive can talk to the parameter I derive using Gaia data. So the star is high speed, is strange, very high speed. Second strange point is very young, again problematic. It's metal poor, of course, and is falling into the galaxy. And okay, I try to derive the surface gravity by using iron 1 and iron 2 instead of using data. And in fact, that's true. The star is becoming higher gravity, so less evolved, if you like. The gravity according to the parallax was 1.5, 1.8. Now it's becoming 2.1. So could it be that Gaia is wrong? Yes, I think now it's wrong. Also because with the two UVES spectra, I understood that the star is in a binary system. Gaia DR3 is not considering it. So for sure, the parallax will be revised in DR4. Is this change in parallax making the star bound? Likely not. We did several Monte Carlo simulations and so on, and just at the edge, the star is bound. But even if it is bound, it's extremely exaggerated in the kinematics. Just one point: if you ever work on external galaxies and so on, one information: the star is normal from a chemical point of view, from nothing to be said except oxygen, high oxygen. So if one day we find a high oxygen external galaxy, okay, this star is perhaps arriving from there. Okay, last point is last summer I had a colleague, Pasquale Panuzzo, who arrived in my office with a Hermes spectrum and said, could you analyze the star? Yes, of course. It was really a boring metal poor star. Boring. Metal poor, but not what I like, just minus 2.5. Nothing to be said. Then he brought me another spectrum. Look at this Sophie spectrum. Again, same boring star. Okay. And then he found out in the ESO archive, fantastic ESO spectrum, and said, look at this one. Again, it's boring. All spectra are boring. The star is completely uneventful. Just to show you how uneventful is this star, this is the UVES spectrum. Why this range? Because here you could see some sort of activity in the star if there would be. Just to say, in the sun, I see a tiny emission in the core. Nothing at all. Also, I checked carbon 12 from the 13, nothing to be said. The only tiny point, okay, it is a bit enhanced in europium, as many metal poor stars. So at this point, I start to be curious. I said, Pasquale, what about this star? What am I looking for? Well, you are looking for, sorry, this is a spectrum, just the quality, and this is the carbon. So yeah, this boring, nothing to be said. Boring, all just to convince you, nothing to be said, and Europe as well. So what is wrong with this star? Well, I had the spectrum already shifted at the correct radial velocity, but anyway, the spectra I investigated are here. So the radial velocity was very similar for the spectra because the UVES, yes, because I don't know, was observed in close time. But what was changing was the radial velocity overall around 2018. So this star is in a binary system. We don't see the other one in the spectrum. We don't see anything from the other one, no emission, no activity, etc. But the other guy is extremely massive. So something like 33 solar masses. So this job started because Pasquale Panuzzo was validating Gaia, saying, okay, is it correct? No, something is not working on this one. So it's correct. We have to investigate on this one. And we investigated. In fact, this one is at the end, one of the three strange systems found. This is called BH3, BH2, BH1. So there are three stars that are orbiting around a black hole. A black hole, but this one is 33 solar masses. So extremely interesting. One point I would say extremely interesting that these two, the masses, I don't recall exactly, there are 8 or 10 solar masses, but this one is 33. And which is the difference? I didn't have the spectra of these two, but apparently they are solar metallicity or something like that. This is metal pool. Why it is so important? At the time, I didn't know when I did the investigation, because I think you know, you work on Gaia here, but it is full of embargo. There is nothing you can know. Everything is secret. So I'm in the DPAC, but yeah, I knew the information very late. But apparently, what I understand is that it's extremely difficult to form a black hole of such a mass, except if you are in a metal pool condition. And in fact, this star, the companion, is in fact metal pool. So this is, we are confirming an expected theory of this star. This was in the press release of, at the end, we have the Gaia collaboration, Pasquale Panuzzo et al. And these are the 3 objects found, and this is the number 3. It also is happening to be in a stream, and I think the archive paper was out last week or something like that. So this is the mass of this one. And in fact, if I understand correctly here, it can be metal rich with no problem. But at this point here, the fact to have good spectra and to have the confirm that is metal pool, I think change it very much. On the other side, also to confirm that there is no emission or anything else. So this star is not interactive with the companion and was not affected by anything from the companion, an explosion or whatsoever. And thank you very much. To conclude, it was just one of the pictures that we celebrated the 10 years of Gaia. It was not of Gaia data acquisition, but Gaia launch. And it was in December, and we had several papers collected, and it was my contribution on the Gaia, so we were very happy on that in my laboratory. Thank you very much.
Elisabetta, what are the odds of these presumably young stars, high velocity stars? Because we should have quite peculiar odds.
A bit, we didn't find a match with anything. So no match from a globular cluster from we search for it. But of course, when I mean, you can go back in the past and say, okay, at 3 sigma, it can come from here and here. We check the metallicity on the possibly globular cluster, but nothing peculiar. But there is a theory where they come from. We have, and we are trying to check it. It's not a secret. Francois Maire is thinking that in falling of the dwarf galaxy trigger a star formation, and we think these are the stars formed at that time. So we also found in Sculptor.
They may also be from a star forming galaxy that plugs into. I'm thinking about the Leo P or Leo 4. We have very tiny metal pool scale dwarf galaxy around the local group, and it's not so crazy that one of them would have splashed in while it was star forming, leaving young stars, young metal pool stars around.
Yeah, I think we should. I know many people are skeptical about it, but I think we should really check many of these galaxies and make statistics and try to understand, because I mean, for me, it was a bit of a shock.
Well, it's strange, it's curious, but it's not out of order. It's possible. There are many possible hypotheses to explain.
But is the period consistent with the age of the star?
Is the
Period of the orbital period of the galaxy?
you don't have the orbital period, but if you imagine Leo P has this metallicity, no? And imagine that you have one that has evolved into the galaxy.
Yeah, but it had to do so within the last 2 gigayears if the age of the star is 2 gigayears.
It
Yes.
has to, so what, the reality, for
So,
sure.
in that direction of the water.
Yeah, yeah. But if this happens, the galaxy is not more there.
Yeah.
Because it's zero.
So I have one about zinc, it is metal origin, is that could be a signature of pair instability supernova nucleosynthesis, but it could also be due to the problem that a normal massive star explode as core collapse or supernova. And so I guess there is no way to discern between the two scenarios.
I don't think we can. I mean, I try to, I work with Stefania Salvador a long time, etc. So we try, I don't say that we search for them, sometimes yes, but anytime we find the zinc full star, we alert, okay, this can be interesting. And then from a theoretical point of view, how formed, etc. I think many possibilities are there, of course.
Yes.
Penso che possiamo sentire la
Sì.
yes, you can ask the question.
May I ask, can you hear me?
Yeah.
Sure.
Okay. So thank you, Elisabetta. I have a general comment. You mentioned that, I apologize, I could connect late in your talk, so I missed the first part. But you mentioned that to have a black hole with a mass of 33 solar masses, you necessarily have a progenitor of low metallicity. This is, of course, true, but not necessarily in the sense that, for example, a 120 solar mass star with solar metallicity ends up its evolution with a total mass of around 30 solar masses. So if this star directly collapses to a black hole, you have a black hole mass of 30 solar masses. So the fact that, of course, for low metallicity progenitors, you expect a massive black hole, this is certainly true because of the lowering of the efficiency of path loss at low metallicity. But this, you can have black hole as massive as around 30 solar masses, even in solar metallicity progenitors.
Thank you. Honestly, about black hole, I know zero. I mean, I read the paper before it was submitted.
Yeah.
But also, I think that I asked myself, could it be that anyway you can merge stars, several black hole neutron stars, and reach these masses? So, from my point of view, investigating a companion, this is just 33 solar masses, something that I can't see that is there. So I agree, but I think I would be nice to try to understand a bit more of these guys. Unique, are there several there? They merged, but this is metal poor. At least we are sure about it. There is also another point. Was the star exactly with this nowadays black hole in the past, or was accreted later?
Yeah,
Accreted,
that's true.
Say trapped is better. Capture. Thank you. But in this case, you can say probably, if it is so, probably was in a cluster. So if the star was not the companion, was in the same cluster. So similar metallicity. So I think there are many questions that will arise on this one. And to the large majority of them, I won't be able to answer. Yeah,
I agree, totally agree. But my comment was just a warning in the sense that it's not necessarily true that a black hole mass of 30 solar masses is necessarily linked to a low mass progenitors, but I agree with you that there are many things that are still unclear in this case. Thank you.
No, thank you for telling me, because this for me was an opportunity to learn something in a field on which I'm zero. So it was really a chance.
there are no other questions, we can thank Elisabetta. And Piercarlo's turn. Piercarlo got his PhD in Trieste, in Sissa, then he spent some year at the Observatory of Trieste. And then he moved to Paris, where he was also the director of Observatory.
No. I was director of GEPI.
No, it's not much. GEPI.
Too much. Observatory has a precedent.
And is now he has an ERC advanced grant on a technological project. Okay. And but today we talk about science and more science oriented about metal quasars in the galactic heavens. Floor is yours.
So thank you very much, Donatella, and thank you. It's always a pleasure to be here in Bologna. So I will try to talk about the metallicity distribution function. So let's start from a historical perspective. At the end of the 1950s, it became clear that not all the stars have solar chemical composition. And Bade introduced the concept of star population, population 1 and population 2, and it was clearly understood that population 2 is low metallicity and population 1 is high metallicity. Now, one was confronted to the problem of quantifying what is this metal content, and it was at the time it was already possible to do abundance analysis using high resolution spectra, but this was extremely time consuming. And in 1962, George Wallerstein very robustly showed that the ultraviolet excess, which is familiar to the diversely young, but perhaps not so familiar to the younger people, is very well correlated with metallicity. And to my knowledge, the same year, Sidney van den Berg published what is the first metallicity distribution function, which in fact he published a distribution in ultraviolet excess. Be careful that on the right you have the metal poor stars, on the left you have the metal rich stars. Okay, so it's vice versa with what I would plot nowadays. So observationally, you have two main problems. So you have to derive some reliable metallicity estimate, at least in a relative sense, for a large number of stars. I put a question mark because large, the concept of large is evolving in time, of course. And then you have to take into account biases that you introduce, because you're not measuring the metallicity of all the galaxy, and therefore you have somehow to select the stars you're looking at, and you introduce biases into it. So the two main approaches that have been used are either to use some photometric estimate. Initially it was ultraviolet excess. So this is lower precision, but very large numbers, or larger numbers. Or you can use spectroscopic estimates. They can have higher precision, question mark, if you do your analysis carefully. And you have smaller numbers, again, question mark, because nowadays with instruments like Gaia RVS, the numbers become huge. So it may be that there are some spectroscopic surveys that are comparable in numbers with photometric surveys. From a theoretical point of view, one is immediately confronted with the question is how metal poor can a poor star be? And this is linked to the question of what was the initial mass function of the population 3 stars. So first stars must have been formed from primordial matter, which is made only of hydrogen, helium, some traces of lithium. And can stars of this chemical composition be observed? So it depends where and when. So in principle, they could be observed very high redshift at the time they are formed, the very massive stars. Or they can be observed in the local universe if they are low mass and they have a very long lifetime, if they were formed at all. So there are both theoretical and observational arguments in favor of the fact that the initial mass function of the top 3 stars was top heavy anyway. So back in 1986, Roger Cairel, in a paper from the humorous title is "Where are top 3 stars?" in fact showed that a small gas cloud of the mass of current day globular cluster can be very quickly enriched to 0.2 of solar metallicity. And so in modern, so this result remains valid. So you very quickly you enrich the gas. So nowadays we call these mini halos. We put a lot of dark matter into them. And here on the right, you can see what is the current view on galaxy formation. So you form small galaxies, and then these progressively merge into something bigger, like the Milky Way. Here are some more recent metallicity functions, both spectroscopic, different approaches. Laird, Carnian, and Latham used high resolution spectra, but very low signal to noise. Initially used only for radial velocities, something taken for radial velocities, something like Gaia RVS, in fact, but high resolution. And they came up with an MDF, and you see they went down to -3 metallicity. There are 2 peaks in this MDF. They did not comment on it. My interpretation, I'll come back to this, is that the lower metallicity peak is the thick disk, and the higher metallicity peak is the thick disk, and the lower metallicity is the galactic halo. Ryan and Norris used a different strategy, low resolution, signal to noise somewhat higher, fewer stars, but pre-selected from photometry, therefore biased sample. But you could see already that they had a metallicity distribution function that extended down to -4 metallicity. So one breakthrough came from the Hamburg-ISO survey led by Norbert Chrisley. Starting from the objective prism spectra taken with the ISO-Schmidt telescope, they selected stars to be observed with different telescopes and spectra, and they came up with a metallicity distribution function which arrives at -5, essentially. And I'm showing these. I'm now showing you the ones with which I want to compare. So the Hamburg ISO is one of them. So since 2016, we have been working at CFHT with the pristine survey. So we use a narrow band filter centered on calcium H and K. And you see in these plots how the lines are metallicity sensitive. The most metal poor you get, the weaker the lines, and you can obtain a metallicity estimation which is fairly accurate if you combine this with some broadband colors. In this case, I'm showing you with Sloan colors, and I would like you to note that the hotter the star, the warmer the star, the closer the isometallicity lines become. So it becomes more difficult to distinguish the metallicity. Then from this, Chris Joachim, at the time PhD student, determined a pristine metallicity distribution function. So he did some color cuts to remove stars which we thought were obviously young disk or horizontal branch stars. You see, apparently this photometric metallicity correlates very well with spectroscopic, but I would like you to focus on the metal poor end here, and you see that the correlation is not so high. If I cut out the metal rich end, it becomes a little bit of a scatter plot, and this precisely for the reason that I was telling you, that the isometallicity stars lines becomes closer. So in the end, so I did not mention, but Chris concentrated on turn-off stars. Why? Because there are many of them. Okay, so you have good statistics. And this was based on 80,000 stars. And I'll compare with them more very quickly. Even more recently, there is this H3 survey, which is conducted with the multi-object spectral effector shell at the multi-mirror telescope. They have a small spectral range, very mild color cut and observed at high latitude. And this is the metallicity distribution function that they derive for a relatively small sample, I would say, 4,200 stars. And as you see, they do not extend to very low metallicity. In their sample, there's no -4 metallicity stars, which does not mean that they do not exist. And this is where we come in. So Elisabetta has designed and has been leading this TOPOS survey. And the idea was to detect metal poor stars. And we started using the French and Italian ink-shooter GTO time to validate the concept, and then we went up with a ESO large program plus other programs at ESO and also at Subaru. And our point was to select extremely metal poor stars and determine their chemical abundances. And we were very successful in this. And essentially what we did, we started with the Sloan spectra, and we had our own analysis tool. We did not rely on the Sloan metallicities, but we derived them directly from the spectra. And as you see, at very low metallicity, essentially the calcium K line is the only metallicity indicator that you have at this low resolution. But still, it turned out to be extremely positive. And we detected many metal poor stars. I think at least a third of the stars below -4.5 were discovered by us, or even pre-discovered. But there's more that we can do for this sample. So the fact is that, after all, we have a very large sample of spectroscopic metallicities. And so we said, this is a good way to determine the metallicity distribution function, at least the metal weak tail of the metallicity distribution. So initially, the stars were selected using Sloan photometry, and this is what we down selected them using Gaia photometry. So we threw away all stars for which there was not a tight correlation between the Sloan and the Gaia photometry. And we end up with a fairly large sample. And we compared our low resolution metallicities with external metallicities, mainly from ourselves, with high resolution, but also other people in the literature. And we have an overall good correlation, even to very low metallicities. Okay, remember what I showed you before of the photometric metallicities of pristine. So the problem is, how do we correct for bias? Everybody knows that Sloan is highly biased in favor of metal poor stars. So because you have to decide to put fibers and then you introduce a large bias. So here's the idea: photometry to the rescue. So go back to the idea of the ultraviolet excess. You do something like that using the Sloan colors, and you see that at least to metallicity -2, there is a reasonable correlation between metallicity and color. And if you compare the spectroscopic metallicity with the photometric metallicity, there is a huge dispersion, but look at the dark points here. So most of the stars lie along a fairly tight correlation. So we're perfect. So the spectroscopic sample is less than 2,050,000 stars, which is still large, but the photometric sample is almost 13 million. Okay, of course, the photometric sample goes deeper, therefore the volume is larger, but we don't think there is a major difference here, and so you can build these two MDFs, and you see the difference between the two. So the photometric has only one peak at fairly high metallicities. Where are the metal-rich stars, solid metallicity stars? They're out. This sample is, and you can see here, disk is out, essentially. Okay, we're observing they're too faint, we're observing too far from the disk. So that's not represented. And we see no, you see, it's obvious here the bias, the huge bias of the SDSS spectroscopic sample. But if I have these two distributions, I can just divide them out, and I can compute what I call the bias. Okay, and then I multiply my spectroscopic method distribution function times the bias, and then you see the second peak, which I assume is the halo, becomes this little bump on the wing of the MDF. And so this is my MDF. Now I can compare with the other MDFs I want to compare with. So essentially Hamburg ISO, pristine, and H3. Now, interestingly enough, H3 agrees very well with the Hamburg ISO down to where it goes, to -3. They have no more multiple stars. Instead, both pristine and our MDF, they are out. On the other hand, once we start correcting for bias, and the other surveys have their own recipes, except H3, that is supposedly, the authors say that they are unbiased, and I believe them. And this shows very much what it looks like, is that, in fact, our MDF goes very in good agreement with H3 down to where they arrive, except we extend to much lower metallicities. Now, my take is that Hamburg ISO, as is, no correction, H3 and our SDSS corrected, they are on the same scale. Therefore, I can average them. And the advantage is that now, for the first time, I can have the error on each point of the MDF. So we can have this error on the MDF, the fact that the errors increase below -3 essentially is driven by two facts. First, the metallicities are less accurate, of course, in all the surveys, but more importantly, there is no H3 there. There's only Hamburg ISO and SDSS. So this is something that you can compare with your models and take into account the errors. So we can do a little bit better. We can actually build three-dimensional maps of the bias. How do we do so? We choose two spatial coordinates, cylindric radius on the galactic plane, and the modulus of distance from the galactic plane, and then you can divide into annuli, and then in each, in such a way that in each annuli you have enough stars, and then you can compute the bias function. And here's a visual impression of what is in different metallicity beams and how the bias changes with galactic coordinates. Now, once you do this, you can actually take your MDF, correct it for the bias, and you can build metallicity maps. And it's interesting, I'm showing here 4 big metallicity beams, and you see how the centroid of this, the peak of this population moves at different places in the galaxy as you move. So this material is not yet analyzed, but hopefully will be sometime. So another interesting thing is that I can try to derive the MDF from subsamples of the Milky Way that have different kinematical properties. So one important bit of the Milky Way is this past accretion event, the Gaia sausage Enceladus, or GSE for short, that you can define kinematically on radial action and LZ, for example. Other people can have other solutions, other definitions, etc. One thing you have to bear in mind is that if you do a purely kinematical selection of GSE, you will have some contamination, and we estimate the contamination in this case to be about 18%. But having done this, I can compute all the kinematics for all the stars, and then I look where they are in space, and I correct the beams for the bias using a 3D bias. Okay, so in this way, I can have, you see, I have the raw metallicity distribution function of the GSE and the correct, which is the one in red. Now, there have been two other MDFs of GSE which have been published, and we disagree. Our MDF is much more metal poor, but there is one fundamental difference, that we are based on turn-off stars. Both these estimates, both Diane Fourier and Richard Naidu, they use giant stars. Does this have an effect? I would say most probably yes. Conroy wrote to me after we published the paper, because I mentioned that one problem is that the flux is different in the sense that the evolutionary time is different from according to metallicity on the RGB. And he said they computed that, although they did not publish it, and that's can account for 0.05 dex of metallicity. He's probably right, but I mean, something is going on there, clearly. So this is something that still needs to be investigated. But the important point is that when you compare the MDF of the GSE with that of the Milky Way, whether you correct it for bias or you don't, you end up with the conclusion that a GSE has many less metal poor stars than the Milky Way. So I think that's an important information to keep in mind. And I think that's fairly robust. And of course, if you take the other MDFs, that would be GSE has 0 stars there, 0. Okay. One last thing is, as I said, much of this hinges on what is the initial mass function of the POP3 stars. So this figure is taken from Ishigaki and collaborators. So from the chemical composition of the extremely poor stars, we can estimate what were the masses of the POP3 supernova that produces these elements. So we know fairly well what is the MDF between 10 and 100 solar masses. However, on the two ends here, this is the domain of the parent instability supernova. We know essentially nothing. And in the low metallicity or low mass end, again, we don't know if there is anything. So this is the metallicity of the Caffau star, which is still the record, the most metal poor object in the universe. So we know we can have masses of that chemical composition. Can we have lower metallicity? We yet do not know. And grazie.
Yes, I have a question on the comparison between GSE and the other MDFs. Yes. So does the bias correction worsen the difference between the peaks, or
no? It improves.
It improves.
You see, without correction, it's the black. Therefore, I'm even more metal poor. So I come near. There is still over a 0.5 dex. So I did one. So one of the difficulties is that neither Naidu nor Foyet published their sample of stars. So you cannot compare, make a one-to-one comparison and see if there is common things. But one thing I did is to take the, Foyet uses the SkyMapper metallicities based from from the Casagrande calibration. So I took for my stars, for which I have spectra, I took the Casagrande calibration and I determined the metallicities. I tried to see how these compare. It's a scatter plot, but it doesn't mean anything because my stars are turn off, those stars are giants. So it may well be that the Casagrande calibration works well for giants, but not for turn off stars. So I don't know, but there's nothing obvious. Once Foyet or the H3 survey eventually will publish all of their results. So once we can, and our results are already available at CDS for all the kinematics, the abundances, etc. Once we can actually compare the two things, perhaps we can come up with ideas how that comes in play.
As you know very well, also our metallicity distribution with strong strong photography agrees with Fourier and I do. But again, it's made just of giants. So a direct comparison cannot be done. But I think you can try to do a direct comparison of your dwarf stars with other samples, larger samples of photographic velocity, like the one by Andra et al., but there are several that include dwarfs, possibly including Pristine, but Pristine as a bias.
Yes, in fact, I want to revisit the Pristine metallicity distribution function, because I think one thing we are doing wrong is that Chris and Elsa decided not to use the Gaia parallax, but rely on color cuts to remove the white dwarfs. Now, having observed, looked at many SDSS spectra of turn of color stars, I can tell you we find a lot of white dwarfs. And many white dwarfs are the ones which have calcium K line absorption. You know, these stars which have eaten planets and etc. And so that kind of absorption will fool Pristine. But if you use instead the Gaia parallax, you totally cut out the white dwarfs. So I would like to redo this using not Sloan colors, because one problem is also the Sloan colors, which are not accurate enough at these low magnitudes, especially as I showed for the turn-off stars, the isometricity lines close off. If I use the Gaia photometry, which is typically, typically it can be millimag accurate, or at least a few hundreds of mag, a lot better than Sloan. So I think we have I would like to redo this fact.
Yeah, so just another follow-up on this. How does the metallicity compares with, for example, star formation history is derived from Columbine to diagram? Or because I was thinking, what if you plot an isochron with your metallicity on this, the Gaia CMD of the Gaia Enceladus stars?
For the GSE, I don't have that, but
I mean, it could be a very quick double check to see how much the age of the Enceladus or other parameters.
But this is the global picture. This is all where our sample star stays. So the weakness of our sample is that it's all here. Okay, so you don't have very much. You have a degeneration between metallicity and age.
Yeah, no, I was thinking, you know, the WZO CMD,
yes,
the famous one. So if you plot an isochron with the metallicity of your peak on top of that CMD, is it completely off? Or would you have to change the age crazily too much to get
a good suggestion? I have to do that. I've not done it. So I have to check that. Yes.
Okay. I think there are no questions online. So if there are no other questions, we can thank you for coming. Ma senti Piercarlo, la diffusione può giocare un ruolo quando vai a vedere la dietro delle giganti rispetto a quella delle navi?